Since its launch, the James Webb Space Telescope has captivated the world, revealing the first light of the universe and the intricate details of distant nebulae. It is, by all accounts, a masterpiece of engineering. However, it faces a fundamental limitation, one that it shares with its predecessor, the iconic Hubble Space Telescope. If you wanted to map the entire sky with the precision of Webb, it would take centuries. Both Hubble and Webb are deep-field specialists. They look through a cosmic keyhole, see the smallest, most distant details. But what if we need to see the big picture? What if we need to understand not just one galaxy, but how billions of them are distributed across the fabric of space-time? This is where the next titan of astronomy comes in. It's a mission designed to solve the greatest mysteries of the cosmos: dark energy, dark matter, and the search for thousands of hidden worlds. Today, we are exploring the next frontier of NASA's great observatories. James Webb and Hubble are about to get a new friend, the Nancy Grace Roman Space Telescope. Before we dive into the incredible technology of this machine, we must understand the woman whose name it bears. Nancy Grace Roman was not just an astronomer. She was NASA's first chief of astronomy and the first woman to hold an executive position at the agency. And she is widely remembered as the mother of Hubble. Naming this telescope after her is more than a tribute. It is a recognition of her vision for panoramic science. While she spent her life ensuring we could see clearly into the void, this new telescope ensures we can see widely. At first glance, the Roman Space Telescope might look familiar. It features a primary mirror 2.4 meters in diameter, exactly the same size as Hubble's. But do not let that similarity fool you. The magic of Roman lies not in the size of its eye, but in the power of its retina. Roman is equipped with a 300 megapixel wide field instrument. To put that in perspective, while Roman has the same resolution and clarity as Hubble, its field of view is 100 times larger. NASA uses a brilliant analogy to explain this leap in capability. If Hubble were looking at a single bacterium on a microscope slide, the Roman Space Telescope would see the entire slide in a single snapshot without losing any detail of that bacterium. This panoramic vision changes the math of astronomy. To capture the famous Hubble Ultra Deep Field, the Hubble telescope had to stare at a tiny patch of sky for hundreds of hours over many days. Roman can capture an area of the sky equivalent to the Ultra Deep Field in less than half an hour. This means that in the first few months of its mission, Roman will map more of the sky in high-resolution infrared light than Hubble has in over 30 years of operation. Why does the Nancy Grace Roman Space Telescope need this massive field of view? The answer lies in the most known substances in our universe: dark matter and dark energy. We know that the expansion of the universe is accelerating, pushed by a mysterious force we call dark energy. We also know that galaxies are held together by the invisible gravity of dark matter. However, because these forces are invisible, we can only study them by observing their effects on a cosmic scale. Roman will act as a cosmic cartographer by observing billions of galaxies across vast stretches of time and space. It will create a 3D map of the universe's evolution. It will look for weak gravitational lensing, a phenomenon where the gravity of dark matter slightly warps the light of galaxies behind it. By measuring these subtle distortions across millions of images, Roman will allow us to see the distribution of dark matter. Furthermore, by measuring how the distribution of galaxies has changed over the last 10 billion years, it will provide the most precise data ever recorded on how dark energy is pulling the universe apart. This could finally tell us the ultimate fate of our cosmos. Will it expand forever, or is there a big rip in our distant future? While Roman looks outward at the structure of the universe, it will also look inward to our own Milky Way galaxy to find exoplanets, planets orbiting other stars. Roman will use a technique called gravitational microlensing. This relies on Einstein's theory of general relativity. When a foreground star passes in front of a more distant background star, its gravity acts like a magnifying glass, brightening the light of the background star. If that foreground star has a planet orbiting it, that planet will create a secondary blip in the light. Because Roman can monitor hundreds of millions of stars in the crowded center of our galaxy simultaneously, it is expected to find thousands of exoplanets. Specifically, it will in planets that are far from their stars, the cold planets that are difficult for other telescopes like Kepler or TESS to detect. The telescope carries a coronagraph instrument. This is an incredibly complex system of masks and mirrors designed to block out the blinding light of a star, allowing the much fainter light of a planet orbiting it to become visible. NASA describes this as trying to see a firefly hovering next to a lighthouse from miles away, meaning it's a prototype for future missions that will eventually search for chemical signs of life, like oxygen or methane, in the atmospheres of Earth-like planets. It is a common misconception that new telescopes replace the old ones. In reality, the most profound discoveries happen when these instruments work in harmony. We are entering the era of the Big Three. Think of it this way. Hubble provides the beautiful, sharp details of the local universe. James Webb zooms in on the most distant. Nancy Grace Roman provides the context. It finds the rare objects, the strangest galaxies, the most distant supernovae, and the oddest planetary systems, and then tells Webb and Hubble exactly where to point their narrow, high-power lenses. Without Roman, Webb is searching for needles in a haystack. With Roman, we have Agent Magnet to find all the needles at once. Together, these three observatories represent a unified front in our quest to understand the laws of physics and our place in the stars. The Nancy Grace Roman Space Telescope is currently scheduled for launch no later than May 2027. It will sit 1 million miles away from Earth at the second Lagrange point, the same stable gravitational spot occupied by James Webb. From that vantage point, it will begin a 5-year primary mission that will redefine our understanding of the large-scale structure of the universe. It is a testament to human curiosity and the legacy of a woman who believed that the stars were meant to be studied, not just admired from afar. We are on the verge of a statistical revolution in astronomy. We are no longer just looking at the universe. We are measuring it, mapping it, and finally beginning to understand the dark forces that govern it. If you found this deep dive into the future of NASA's missions fascinating, make sure to hit the like button and subscribe to the channel. We'll be following the Roman mission every step of the way. To clarify, I know that in this video there were mentioned many topics that I couldn't explain in depth, but you can comment if you want more information and I'll make a video about it.